Hello, AP Chemistry, and welcome to special topics from Chapter 17. Like I said in class, you're only going to read the specific parts of Chapter 17 that correspond to the whatever page numbers and sections I give you in the outline. The rest of Chapter 17 will lump into the next chapter. Okay? So, Ksp, right, is a special kind of K where the SP means solubility product constant, right? So when we say Ksp, we're talking about the equilibrium constant, but more specifically, the solubility product constant, okay? Same idea, though, right, where K is an expression of basically the amount of product raised to their coefficients over the amount of reactant raised to their coefficients, except that it corresponds to a specific situation, right? In this case, it's the situation where a solid salt, dissolves in water to form ions, okay? Where a specific solid salt, dissolves in water to form ions, right? Now, let's talk about some of the salts that we know. So for example, right, if we have NaCl solid, right, and that's going to form sodium ions, and it's also going to form chloride ions, right? Now, let's take another salt, for example. Let's say we have this. All right. What do you notice about these two dissolving equations? Right. A huge part of you would be like, yeah, sodium chloride, totally, yes. Lead chloride, that's on our list of ding, 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 solubility rules as being a precipitate, right? As being insoluble, right? Based on everything we talked about last year, right, this is considered an insoluble compound, right? Now, what that really means, insoluble, just means sparingly soluble, right? It means that when we put lead chloride in water, we're going to see a bunch of solid, but there is a tiny, tiny amount of solid that is going to dissolve and exist in equilibrium, right, as long as some solid is present, with its ions, right? So when we say that an ionic compound is insoluble, all that really means is it dissolves only a tiny, tiny, tiny little bit, right? And as long as solid is present, it's in equilibrium with its ions, okay? Whereas for sodium chloride, for example, as long as we are below the solubility threshold, right, this is just a forward process, right? There's no back and forth. If we were thinking about a K value for this, what would it be? Right, something astronomical, right? Because it's pretty much all product with little to no this, right? And there is no back and forth, yeah? Here, though, right, we're going to have tiny, tiny Ksp values. Now, if we're going to write a Ksp equation for this, right, it would look like yes, right? Fantastic, because we exclude the solids. All right, so when you're asked to provide a Ksp expression for a salt dissolving in water, right, this is always what we're talking about, right? Ksp equals ions raised to their respective coefficients. All right, which will have the greatest molar solubility, right? Really, really important. When we say a Ksp value, so Ksp equals 1.8 times 10 to the negative 10, that is the K value that defines how much ion we can form, right? That is not the number that represents how much ion we form, right? Where solubility is how much of the ions will form, basically, right? Where the ions that form go back to how much of the original dissolved. So, for example, if we're talking about AgCl, solid, forming its respective ions, right? This is my equation, right? That means my Ksp looks like Ag and Cl, right? And I know that this equals 1.8 times 10 to the negative 10, right? Which means that if I were solving this equation, right, this would basically say x squared is equal to 1.8 times 10 to the negative 10, right? And then if we'd solve for x, we would get, oh, by the way, we would solve for x by doing what? Right, taking the square root of everything on both sides, right? Where that basically means this, right? Now, if I were going to ballpark that, I know that this is going to be on the order of, right, 10 to the negative 5, because If I raise it to the 1/2 power, which is what square root means, right? 10 times 1/2 gives us something on the order of -5, right? And then the square root of whatever that is, okay? But we're going to say something on the order of 10 to -5. So that means my solubility, this is representing, right, how much of these dissolved. Where if we think about our mole ratios, right, whatever this is a 1-to-1 ratio with how much of this did dissolve, yeah? So then the solubility of AgCl is somewhere on the order of 10 to -5 molar. Yes? Fantastic. All right. So then, if that's the Ksp for AgCl, and we think about the Ksp for AgBr, right, being 10 to -13, or this one being 10 to the -17, right, which compound has the greatest molar solubility? Right. These exponents are just going to get smaller and smaller, right? Or no, bigger and bigger, which means smaller and smaller, right? Which means that this one has our greatest molar solubility, yeah? Make sense? Okay, because again, going back to what Ksp means, right? Things that dissolve well will have giant Ksps. Things that don't dissolve well will have tiny Ksps, right? Where again, for this particular process, right, Ksp, right, K is going to be my ions, just my ions, right? Yeah? Okay. Moving along. Let's do a practice problem. So it says a saturated solution of magnesium hydroxide in contact with undissolved MgOH2. What's the significance of that part? Right. This is the part that tells us we have an equilibrium situation, right? Because we have to have all the components present in order for it to be an equilibrium condition. Okay, the pH, oh, look, pH, fancy that, of the solution is found to be 10.17. Assuming that the magnesium hydroxide dissociates completely in water and there are no other simultaneous equilibria, things we'll talk about later, involving the magnesium hydroxide, calculate Ksp. So important things to note. One, right, all of the ions come from magnesium hydroxide, right, which is why there's no other things happening, right? There is no other source of magnesium or hydroxide ions, so there's nothing else to consider. All the ions come from the solid that we added, okay? Now, let's go ahead and start with some important things, right? So this is important, right? We need to know this. So we know that we have this is in equilibrium with this, right? We also know that the Ksp for this says this and this, right? What are we looking for? Oh, we're looking for Ksp. Okay, so we know that, right? We also know that pH is equal to 10.17. Now, what is pH a good reflection of? Or how do we solve for pH? Right, it's the negative log of the H plus concentration, or the hydronium ion concentration. Now, is that really useful for what we're talking about here? No, we're talking about hydroxide, but right, pH plus pOH has to equal 14, right? Therefore, we know that the pOH is equal to, right, 3.82, 3.83. This says 3. Okay, now, what can I do with this now? Right, 10 to the negative 3.83 is going to give me my hydroxide ion concentration, right? So it's going to give us something along the lines of 1.5 times 10 to the negative 4 molar, yeah? Okay, so I know that this is my concentration of hydroxide ion. So let's think about what that means, okay? Thinking back over here. If this is the concentration of hydroxide ions, and I know that all of these ions came from here, what does that mean about the concentration of magnesium ions? Right, it's half that, yes? Okay, so then I know that for my Ksp expression, I'm going to say that my magnesium ion concentration is half of this. So if that's 1.5, then it's going to be, right, 0.75 times 10 to the negative 4th molar times 1.5 times 10 to the negative 4th squared, and I would solve for this, and that would be my Ksp value. Yeah? All right, next up. Ksp for this is that. What is the solubility? Okay, solubility, right? So we should start here because that's always a good place to start. And then we're going to form this, plus this. Okay, and I know that my Ksp is equal to this times this to the third. Okay, and this is equal to 2 times 10 to the 19th. Now, I'm looking for solubility. So what is it I'm actually looking to solve for? Right. I'm looking for this, which would tie to this, and is in a 1-to-1 ratio with how much actually dissolved, yeah? Which is what solubility is, how much dissolves. So then, what that means is I just have to do a little bit of stoichiometry with a little bit of variable work. So, I know that for every one of these, I'm going to form one of these, yeah? Okay. So then, and this kind of, and depends on how you think about it, right? So you can think about it like an ice table if that's what you kind of see in your head, or you can think about it just as a stoichiometry problem, whatever works best for you, right? But the point is, right, that this is irrelevant, okay? Here though, right, we start off with none of each of these, right? We know that we're going to make, or we're going to dissolve some of this. How much of this are we going to dissolve? Right, 3 times that amount, which means that we are looking for x and 3x as my respective equilibrium concentrations, yeah? Right? So again, if we're just up here, right, we know that if this dissolves, right, we're going to form one of these, 3 of these, yeah? Which is the same thing that this says. So whatever makes more sense to you, right? So then that's what we're going to plug in here to solve for, right? We can solve for one variable. So we're going to say Ksp equals, right, x, 3x to the third is equal to 2 times 10 to the, yeah, that should say negative 19th. The negative's missing. Okay, so then from here, what happens? Right, x times 3x cubed. X times, be careful here, 3x cubed. What's that? Right, don't forget to cube the 3. 3 times 3 times 3, right? So this is times, right? So this is basically 27x cubed, right? And this is x, so I actually have 27x to the fourth is equal to 2 times 10 to the negative 19th. And then I could solve for x, where x ties to this, to that, to that, to that. Yeah? All right. Thank you very much. Be good, and I will see you soon. Bye.